Good morning, everyone. In this video, we shall deal with part 2 of nitrogenous compounds. In the first part, we dealt with the nitro group as a functional group. We dealt with the aliphatic and the aromatic nitro groups. So accordingly, we have already covered number 1, which are the nitro compounds, whether aliphatic or aromatic, in the first video dealing with part 1 of nitrogenous compounds. Today we shall deal with the second part of the nitrogenous compounds, which are the amines. We shall deal with their structure, their classification, nomenclature, basicity, and their reactions. Part 3 will deal with diazonium salts. This will be included in a separate video. First of all, what are amines? Amines are compounds that has a nitrogen in its structure. And there is one more condition, which is that this nitrogen should have its lone pair of electrons localized on it. They should not be involved, the lone pair of electrons should not be involved in a coordinate bond with a vacant orbital of whichever metal. If they are involved in a coordinate bond with oxygen, for example, then this is the nitro group, which is not an amine. It's a totally different functional group. So amines are nitrogens that are singly bonded to 3 other atoms, and they have their lone pair of electrons localized on their nitrogen. They can be involved in a resonance, but they cannot be involved in a coordinate bond. If the nitrogen is carrying 1 carbon, if it's attached or bonded to 1 carbon, then this is the primary amine. If it's attached to 2 carbons, then this is the secondary amine. And if it's attached to 3 carbons, then this is the tertiary amine. If we attach it to a 4th carbon, putting a positive charge on the nitrogen and a counter ion halide should be present, or a hydroxide or whatever, then this is a quaternary amine. So primary and secondary and tertiary and quaternary amines are exactly the same as primary and secondary and tertiary and quaternary carbons. It depends on the number of carbons attached to the nitrogen. Since the nitrogen is multivalent, exactly like the carbon, we actually mean what is attached to the nitrogen when we're dealing with the classification primary, secondary, and tertiary of the amines. As we mentioned before, if the function group is monovalent, we actually deal with the carbon that is attached to the function group. However, in case of amines, we do not have to deal with the carbon that is attached to the amine. We deal directly with the nitrogen of the amine. If it's attached to 1 carbon, then it's primary. If 2 carbons, then it's secondary. If 3 carbons, then it's a tertiary amine. Let's just take one example. If we have a nitrogen attached to methyl groups and a hydrogen, and thus carrying a positive charge, and a halide is present as a counter ion. What is the classification of this amine? Is it a primary, a secondary, or tertiary, or quaternary? First of all, do not get fooled by the positive charge on the nitrogen. We always, in case of quaternary amines, we have a nitrogen carrying a positive charge. So when you see the positive charge, you will immediately think of quaternary amines, which is totally incorrect. As we mentioned, quaternary amines are nitrogens or amines that are carrying 4 carbons. The positive is not the condition here. The condition is the 4 carbons. The positive charge that is carried by the nitrogen is a result of this condition. It's not the actual condition. So now we have the nitrogen attached only to 3 carbons. So this is a tertiary amine. Even though it's carrying a positive charge, it's a tertiary amine. Just look at the number of carbons attached to the nitrogen of the amine. This is the first classification of amines. If we look at the second classification of amines, we will deal with whether they are aliphatic or aromatic. As we all know, if the functional group, which is the amine here, is directly attached to a carbon which is aliphatic, a regular alkyl chain, these are the aliphatic amines. However, if it's attached to a benzene ring, these are the aromatic amine. This is the regular classification that we all know. However, if we have a nitrogen, an amino group, that is attached to an aliphatic chain but has a benzene ring in its structure, is this an aliphatic amine or an aromatic amine? Looking at this structure, it's an aliphatic amine because the amino group is directly attached to an aliphatic chain. However, it's an aromatic compound. So this is an aliphatic amine, but an aromatic compound. So how do we classify such a compound? We say that these are aryl alkyls. So how does the name come? How is this name formed? R is from aryl and alkyl from alkyl, and these are amines. So these are aralkyl amines. What are aralkyl amines? They are aliphatic amines, but they are aromatic compounds. The final classification that we can deal with are the heterocyclic amines. What are heterocyclic amines? Let's look at this name. Cyclic means that you have a ring, whether 5-membered, 6-membered, 7-membered, whichever the size of the ring is, you have a ring. That's the meaning of the word cyclic in organic chemistry. You have a ring. Hetero means that one of the atoms is exchanged by something different from the rest of the atoms. That's the meaning of the word hetero, something different. So what is the common ion the common atom that is present in a ring? It's the carbon. The regular atom that we always have in our rings is the carbon. So all these atoms are carbons. We need to change one of them and replace it by something different from carbons. And since we're dealing with amines, so we are replacing one of the carbons by a nitrogen. If we replace one of the carbons by a nitrogen, these are the heterocyclic amines. So let's look back at the classifications. We had two types of classifications. The first was the primary, secondary, tertiary, and quaternary amines. This is the first classification, where the primary had the nitrogen attached to one carbon, the secondary had the nitrogen attached to 2 carbons, the tertiary had the nitrogen attached to 3 carbons, and the quaternary, the nitrogen was attached to 4 carbons and was carrying a positive charge. The second classification was the aliphatic versus the aromatic versus the aralkyls, and finally the heterocyclic amines. The aliphatic has the nitrogen attached to an aliphatic chain. The aromatic has the nitrogen attached to a benzene ring. The aralkyls has a nitrogen attached to an aliphatic chain. However, the structure contains a benzene ring. And the heterocyclic is a ring that has a nitrogen in its constitution. So, as we mentioned, we have two classifications for the amines. As we said, aliphatic, aromatic, aralkyls, and heterocyclic. This is one type of classification. And the second type is the primary, secondary, tertiary, and quaternary amines, just as the carbons. Now we move to the nomenclature of amines. And as we all know, in case of nomenclature, we usually deal with the common names and the EUPAC names. In case of common names, what we do is that we name the alkane that is attached to the nitrogen. Say if it's 1 carbon, then this is the methane. We say that it's a methyl. We remove the ane and we add an I, and then we put the word amine. So this is a methylamine. This is how we commonly name amines. The EUPAC nomenclature is not much different. You again name the alkane, which is methane, but this time you will not remove the whole ane, you will just remove the E at the end of the name, and you add the word amine. So in case of common names, it's methylamine. In case of EUPAC names, it's methanamine. If you have a substituent on the nitrogen, if the nitrogen is attached to a substituent, if it's alkylated, for example, you will give the substituent the letter N. You will not give it numbers. Numbers only apply to the aliphatic or the aromatic chain attached to the nitrogen. The parent chain attached to the nitrogen. Say, for example, here it's a propanamine. If I add a methyl here, then this is the N-methylpropanamine. How to choose the parent? The longest. You will choose the parent chain that you will consider as the parent chain of the structure. It's going to be the longest chain attached to the nitrogen, and all the other smaller alkyl groups are going to be substituents on the nitrogen. They're going to be given the letter N. They're not going to be given any numbers. A number is usually applied to the substituents on the parent chain, on the propane here. If I add a chloro, then this is the 2-chloro. This is the 2-chloro N-methylpropanamine. So the numbers will be applied to the chain, and a letter N will be applied to the substituents on the nitrogen. So these are just examples on how to nomenclate amines by the common way and by the EUPAC way. As we mentioned, the numbers apply to the chain, parent chain that is attached to the amine. And you just name the chain, you give it its EUPAC nomenclature, and you remove the E at the end of the word alkane, and you add the word amine. If the amino group is not the parent, it's not the highest priority functional group in your structure, for example, you have something like ketones or aldehydes or acids, these are compounds that have higher priority than amines, then you will name the amine part as an amino substituent. So in case of something like that, you have a 6-carbon chain as an acid, so this is hexanoic acid, and then you start numbering from the carboxylic group. This is 1, 2, 3, 4, so on the 4 carbon you have an amino substituent. This applies to all compounds that have an amino group on it. It's either that the amino group is the highest priority, so it's an amine at the end of the name, or if it's not the highest priority and you have a much higher priority in the structure, like carbonyl compounds, for example, then it's a substituent and it's named amino at the beginning. It's going to be a prefix and not a suffix in the name of the compound. Finally, in case of aromatic amines, we have some common names that we have to memorize as such. They have no reasons. They're just named as such. When you have an amino group attached to a benzene ring, this is the aniline. If you add a methyl group to this compound, it's going to be the toluidine. Toluidines can either be ortho, meta, or para, depending on the position of the methyl group relative to the amino group. If it's in the 2 position, then this is the orthotoluidine. 3 position, this is the metatoluidine. 4 position, this is the paratoluidine. We have aniline when it's substituted by 2 methyl groups on the nitrogen of the amino group, then this is the N,N-dimethyl-aniline. If you have 2 amino groups attached to the benzene ring, you will have the phenyline diamines. Again, these can be ortho, meta, or para. The most common is the paraphenyline diamine, where the 2 amino groups are para to each other. We have a compound which contains 2 phenyl groups and an 2 amino groups peripheral, where they are para to the phenyls. This is the benzidine. Finally, we have the anthranilic acid and the sulfonilic acid. The anthranilic acid is an aniline having a carboxylic group, and sulfonylic acid is an aniline having a sulfonic group. But we have to notice here that anthranilic acid is the ortho substituent. The amino group has to be in the ortho position to the carboxylic group. If the amino group is moved to the 3 or to the 4 position, for example, something like that, this is not anthranilic acid. It's not meta-anthranilic acid. Anthranilic acid has no ortho or meta or para preceding it. It's just anthranilic acid, and it means that you have the amino group ortho to the carboxylic group. If you move the amino group to the meta or to the para, this is not anthranilic acid. This is going to be 3-aminobenzoic acid or 4-aminobenzoic acid, and the same applies to sulfonylic acid. Sulfonylic acid means that the amino group is para to the sulfonic group. It's not ortho, it's not meta, and you cannot form the ortho or the meta using the word sulfonylic acid. You're going to say 3-amino benzene sulfonic acid or 2-amino benzene sulfonic acid. It will not have a common name. It's not sulfonylic acid. Sulfonylic acid is only when the amino group is para to the sulfonic group. Now we move to the preparation of amines. First of all, we're going to prepare the aromatic amines. In case of aromatic amines, or in case of amines in general, you usually have a halogen that is attached to a carbon, and you replace it by an amine moiety, where the amino group has the lone pair of electrons. It will attack the carbon, removing and replacing the halogen attached to the carbon. This is one of the very common methods for the preparation of amines. This is the nucleophilic. This is what you have already studied in alkyl halides as the nucleophilic substitution of alkyl halides by different nucleophiles. And here the amine or the ammonia acts as a nucleophile since it's carrying a lone pair of electrons. Let's apply this reaction to the preparation of different amines. If you are dealing with aromatic amines, you're going to have to use an aryl halide. So you're going to have a benzene, and attached to this benzene a halogen. And you should add an amine to substitute this halogen. However, if you remember when we were dealing with aryl halides, we said that the single bond between the chloro group and the benzene ring is non-breakable. It's not that easily breakable. Why is that? Because as we mentioned, the lone pair of electrons on the halogen is present in an orbital which is in parallelism with the p orbitals of the benzene ring. Accordingly, there is an overlap between the whole electronic system of the halogen with the benzene ring, and thus this bond is not really a single bond, it's a partial single, partial double, and accordingly we cannot break it that easily. So how do we break it? If we need to break this bond, what we do is to substitute, in order to be able to substitute this halogen, we use to add strong electron withdrawing groups at the ortho and the para position. This way, the position carrying the carbon carrying the halogen will have a high positive charge due to the resonance of the nitro group. Refer to the part 1 of the nitrogenous compounds, where we were dealing with nitro groups, aromatic nitro compounds, and we said that the ortho and the para positions to the nitro group are usually carrying a positive charge due to the resonance of the amino group, and accordingly whatever is at these positions, whether a hydrogen, a halogen, or another nitro group, can be easily replaced by nucleophiles. So you will add a nitro group at the ortho and para positions of the halogen so that you can easily replace them by the amine that you need to include in the structure. This is how you can prepare aromatic amines. Let's go to the preparation of aliphatic amines. So if we now deal with the preparation of aliphatic amines, we have actually 3 methods for their preparation, 3 major methods. You have already dealt with most of them. I'm just going to specify some nota benes, some remarks on how you perform them. However, you have already dealt with all of them. First method is from alkyl halides, and as I mentioned, you have already dealt with the reaction of amines as nucleophiles with alkyl halides in case of the whole class, which is alkyl halides. The second method is the reduction of compounds that contain nitrogens, and as you know, these are the cyano group. You can reduce it to produce the amino. The nitro group, again, you can reduce it to produce the amino, and the acid amides, which can be reduced to give the amino group. So you already know these. I'm just going to give a few hints about how to apply the reaction. Finally, we have the degradation reactions, and as you know them, we have already studied them in case of amines. These are three types of reactions. We have the Huffman degradation reaction, where you actually use an amide. You use an amide and you add bromine in presence of sodium hydroxide, and the end product is that you remove the carbonyl and you directly attach the amino group to the carbon that was attached to the carbonyl. If you remember, we had two more reactions which were Curtius and Lawson's. In Curtius, you use the acid azide, and again you will end up with the amine directly attached to whichever was attached to the carbonyl group. And in case of Lawson's, you used the hydroxamic acid, which is the hydroxyl amine, and again you will end up with the primary amine. So to prepare primary amines, you have to use you can use to prepare primary amines, you can use one of three major methods. It's either you use the alkyl halides, and we're going to see how these are used to prepare amines, primary amines. You can use the reduction technique, in which you use either the cyano group, the nitro group, or the acid amides. And finally, you have the degradation techniques, in which you use either the Huffman through using the acid amide, or the Curtius reaction through applying your conditions to the acid azide, or finally you can use the Lawson's reaction by using the hydroxamic acid compounds. Let's deal with each one of them separately. First of all, if we deal with the alkyl halides, we have one problem that is preventing us from using a very straightforward reaction, which is applying an amine compound to the alkyl halide. What we should expect is that the lone pair of electrons should attack the R group, replacing the halogen, which is true. However, we have one problem now. The alkyl halide group, as we all know, when we're performing a reaction, you're not using a one molecule of the structure. You're actually using several molecules, millions of molecules. Your container contains millions of the ammonia and millions of the alkyl halide. So now the alkyl halide, but once an primary amine is formed, the alkyl halide will have two options to react with. We'll have the reagent that I'm actually using, which is the ammonia, and the product that I have just produced, which is the amine, the primary amine. Let's look at each one of them. In case of ammonia, the nitrogen is attached to 3 hydrogens, and it has its lone pair of electrons localized in it. In case of the primary amine, you will have the nitrogen attached to 2 hydrogens and 1 carbon. This carbon is electron donating by induction. It produces a plus induction to the nitrogen. So it's increasing the lone pair of electrons on the nitrogen. So this nitrogen has a more localized lone pair of electrons on it than the nitrogen of the ammonia. So if the alkyl halide has to choose to react with which one of them, it prefers to react with the primary amine rather than the reagent that I have just used, which is the ammonia. Accordingly, I can never end up with the primary amine. What I actually end up with is the secondary and the tertiary amines, where the alkyl halide is always choosing the product over the reagent, because primary amines have one R donating electrons to it, while secondary amines has 2 carbons donating electrons to it, while tertiary amines has 3 carbons donating electrons to it. So which one is more basic, which one has the electrons more localized in it? It's the tertiary more than the secondary more than the primary, and accordingly such a reaction will end up with the tertiary and the secondary, and it might even end up with the quaternary amine. Accordingly, we have to solve this problem. We cannot use this reaction to prepare primary amines. We have to deal with a different type of reactions, or we can perform some modifications to the method so that we can prepare primary amines from this starting material, which is the alkyl halide. However, if we need to prepare the tertiary or the quaternary, we can simply use this method. So what are these modifications that we can use? So from alkyl halides, we mentioned that we have a problem, which is we cannot end up with the primary amine. We have to end up, or we actually end up with the secondary, the tertiary, and the quaternary. The reaction proceeds and does not stop at the primary amine formation. So how do we solve this problem? We have 2 scientists, one called Gabriel and the other one called Hoffman. They solved this problem through another reaction, or through different technique. How did Hoffman solve the problem? Hoffman said, if you have an alkyl halide, do not react it with amine, react it with azide, sodium azide. This will give you the alkyl azide, which you can reduce to end up with the amine. So this is the first solution to our problem. Do not use the amine, use the azide. And after you have finished the formation of the azide, the alkyl azide, reduce your product. So it's a 2-step reaction where you first react the alkyl halide with the sodium azide, forming the alkyl azide, and then you reduce it. Gabriel used a totally different technique where he actually used the phthalimide compound. As we mentioned in acid derivatives, phthalimides are compounds that contain an acidic hydrogen. The hydrogen of this compound is acidic. It can be removed by a base placing a negative charge on the nitrogen. And why are they acidic compounds and they can lose their hydrogen? Because once the negative charge is placed on the nitrogen, it can be stabilized by resonance towards 2 carbonyl rather than 1 carbonyl group. So these are the phthalimides. We use a phthalimide. We add a base to phthalimide. We add a base to phthalimide to put the negative charge on the nitrogen, and it will have a counter ion, which is the potassium or the sodium, whichever base you have used, if you're using potassium hydroxide, for example. And then you add the alkyl halide. The negative charge will attack the carbon attached to the halogen, replacing the halogen. Definitely a negative charge in case of phthalimide is much more stronger nucleophile than just a lone pair of electrons in case of an amine. When we were using ammonia, we just had a lone pair of electrons. Now we're actually using a full negative charge in case of phthalimide, which is a stronger nucleophile. So the reaction will proceed more favorably. And then once the alkyl group is attached to the N of the phthalimide, we can hydrolyze this compound and we will end up with the phthalic acid and the alkyl amine, where you actually break this bond and break this bond, placing an OH here and an H here, and placing an OH here and an H here. So you end up with the primary amine, and there's no chance you can form the secondary nor the tertiary because the bonds of the nitrogen, the other two bonds of the nitrogen, are involved in an amide bonding with the imide. Okay, so these are the two solutions for the problem of forming the secondary, tertiary, and the quaternary amines when you are preparing primary amines from alkyl halides. Now we come to the second method for the preparation of primary amines, which is the reduction technique. You can actually reduce, as we mentioned, three types of functional groups, which are the cyano group. You can reduce it to produce the amine. You can reduce the nitro group, and again you will get the amine. And finally, you can reduce the acid amide. If you remember, when we were dealing with acid derivatives, you can revise this part of acid derivatives where we said that in the general reactions of acid derivatives, if you reduce all acid derivatives, you will get a primary alcohol. All acid derivatives, when they were reduced, they produced alcohols, primary alcohols, except for the acid amides. We said that acid amides, upon reduction, they produce primary amines. So you will reduce acid amides using whichever reducing agent you want, resulting into the primary amine. Okay, so this is one method. The second, as we mentioned, is the reduction of the nitriles or the cyano groups, where you actually reduce cyano giving a primary amine. Finally, we have the nitro group. As we mentioned in part 1 of nitrogenous compounds, nitro groups can be reduced by several techniques. The only techniques that produce amines are the catalytic reduction, where you actually use hydrogen in presence of a catalyst, or acid reduction, where you use zinc in presence of acid medium. And finally, you have the selective reduction, where you used sodium sulfide or ammonium sulfide. In case of catalytic reduction, you had a nitro group that you could convert into a primary amine, the same in case of acid reduction. And finally, in case of selective reduction, you had the same thing. You had a nitro group that you actually converted into a primary amine. How to choose which methods to use? It depends on what is present on your side chain. What does that mean? It means that if your side chain contains a hydrolyzable group, for example, like esters, and it has a nitro and you need to reduce it, you cannot use the acid reduction of the nitro group, because you will end up with hydrolysis of the ester. You will not have the R here, you will have a hydrolyzed acid. So this method is not the correct method to choose. You should actually choose catalytic reduction, where you will reduce, in this case, the nitro group into an amino, leaving the ester group. However, if you had a group that is reducible by catalytic reduction, for example, a double bond on your side chain, then you cannot use catalytic reduction, because you will end up with the amine, it's true, but you will also reduce the double bond that was present in your side chain, and you will end up with a single bond. If this is not what you need, then this is not the correct reagent to choose, and you should choose the acid reduction of the nitro group to keep the double bond and not reduce it, and at the same time end up with the primary amine. Finally, in case of the selective reduction, as we mentioned before, it's only used if you have two nitro groups and you need to reduce one and leave the other one. If we now start discussing the degradation techniques, as we mentioned, please refer to the video of the acid derivatives, where we had the special reactions of acid derivatives. I think it was part 2 of the acid derivatives, where we used 3 different techniques. One was the Huffman. This deals with reacting an acid amide with bromine in presence of sodium hydroxide, resulting into the primary amine. The second one was lysins, where we actually used the hydroxamic acid, where one of the hydrogens on the nitrogen was replaced by a hydroxy group, and whether you use an acid medium or an alkaline medium, together with heating, you will end up with the primary amine, where you remove the C double bond O and the OH on the nitrogen. Finally, the Curtius reaction, where you actually use the acid azide, and again by warming you will end up with the primary amine, losing two of the nitrogens and the carbonyl in between the nitrogen and the alkyl group. This is how you prepare primary amines. As I've mentioned, if you need to prepare secondary or tertiary amines, you can actually use direct reaction of the alkyl halide with the ammonia, and you will end up with the secondary and the tertiary and the quaternary amines. The secondary amines have a specific method for their preparation, but I will not mention it here, because in case of this type of reaction you will probably end up with the tertiary rather than the secondary. However, I will just consider that this is applicable and that you can prepare secondary and tertiary amines from direct reaction of alkyl halides with ammonia, and that you can separate or you can stop at the secondary amine. I will just consider that this is possible, which is not true. It has a specific type of reaction, but I have cancelled this reaction from your syllabus to facilitate studying for you. Now we shall deal with the basicity of amines. But first of all, let's first go through the organized slides dealing with the preparation of amines. As we mentioned, if we need to prepare aromatic amines, we place a halogen on a benzene ring, but we have to place two nitro groups, or at least one nitro group, in the ortho or the para positions to the halogen to be able to replace the halogen by the nucleophile, which is the ammonia. These two electron withdrawing groups will place a positive charge on the carbon attached to the halogen, facilitating the reaction. Afterwards, we dealt with the preparation of primary amines, where we said that we have three different methods, either from alkyl halides or through the reduction or through the degradation techniques. We said that in case of alkyl halides, we have the problem of formation of the secondary and the tertiary amines. So accordingly, we had two solutions for this problem. One was done by Gabriel. Gabriel said that you can use phthalimide, removing the proton of the phthalimide using a base, ending up with a negative charge on the nitrogen that can be used to attack an alkyl chain attached to the halogen and accordingly attach the alkyl group to the nitrogen. This is an amine, but it's not formed yet. It's still in the form of an imide. If you hydrolyze this compound, you will end up with the phthalic acid together with the primary amine. The second scientist that solved the problem of formation of secondary and tertiary and quaternary amines when reacting ammonia with alkyl halides was Hoffman, where he actually said that you can use sodium azide rather than the regular amines, ending into the alkyl azides that can be reduced into the primary amine. The second method that we said that can be used for the preparation of primary amines is the reduction. As we said, you can reduce a cyano group ending up into an amine, or you can reduce an acid amide giving an amine, and finally you can reduce a nitro group into amine. And as we mentioned, you can reduce nitro groups into primary amines using one of three techniques: either the catalytic reduction, the reduction in acid medium where you use zinc in presence of acid medium, or the selective reduction where we use sodium sulfide or ammonium sulfide, resulting into a reduction of one of the nitro group and leaving the other one. Finally, we had the degradation reactions where we can use either Hoffman if we have an acid amide, or Curtius if we have an acid azide, and finally lysins if we have a hydroxamic acid. As we mentioned, in case of secondary and tertiary amines, you can just use the alkyl halides with the amines. However, it's preferable to use an aromatic amine to decrease the activation of the side chain to the nitrogen, and accordingly you can stop at the secondary or the tertiary amines. Now we shall start dealing with the basicity of amines, which is a part of their reactions. According to their basicity, you can actually form salts. So this is the factor controlling the first reaction of amines, which is the salt formation. What is the meaning of the word base? A base is a compound that can accept protons. An acid is a compound that liberates or donates protons, and a base is a compound that accepts protons. So to accept a proton is actually a moiety that is carrying a positive charge. So to be able to accept a proton, you actually have to have a negative or a lone pair of electrons or a partial negative attached to the compound. This is available in case of amines on the nitrogen. On the nitrogen, you have a lone pair of electrons. So these are bases. The proton can come and attach itself to the lone pair of electrons available on the nitrogen. So it's a base. The more the lone pair of electrons are present on the nitrogen, the more the basicity of the compound. The less the lone pair of electrons are present on the nitrogen, if we have something withdrawing these electrons away from the nitrogen, the less is the basicity of these compounds. So if we apply this to primary, secondary, and tertiary amines, we will find that in case of tertiary amines, we have 3 electron donating groups attached to the nitrogen by induction. So it will have more electrons localized on the nitrogen than the secondary, which has only 2 donating groups, than the primary, which has only 1 electron group, than the ammonia, which has only hydrogens attached to the nitrogen. This is when we are actually comparing aliphatic amines to each other. Remember that if one of these alkyl chain has an electron donating group, this will increase the basicity, and if it has an electron withdrawing group, this will reduce the basicity of these compounds. Remember, presence of electron donating groups will increase the basicity because it will increase the presence of the lone pair of electrons on the nitrogen. Now, if we look at aromatic amines and we compare them to aliphatic amines, in case of aromatic amines, you have a benzene ring attached to the nitrogen. The lone pair of electrons are present in an orbital which is parallel to the p orbitals of the benzene ring, which means that you actually have a cloud involving the lone pair of electrons of the nitrogen. The cloud, the benzene ring cloud, will include the lone pair of electrons of the nitrogen of the amine inside it. It will keep the lone pair of electrons of the nitrogen in the electron cloud of the benzene ring, and accordingly this nitrogen is not lone pair of electrons, these 2 lone pair of electrons are not localized on the nitrogen. They are more donated to the ring and they are more present inside the ring. So if we compare aliphatic amines with aromatic amines, aliphatic amines will be more basic than aromatic amines. Aromatic amines are very low in their basicity due to the resonance between the lone pair of electrons and the benzene ring. If you add an electron withdrawing group to this ring, you are further decreasing the basicity, and if you add an electron donating group to this ring, you are improving the basicity a little bit. If you add more benzene rings, for example, if you are comparing aniline with the diphenylamine, where you have 2 benzene rings attached to the nitrogen, compared with the triphenylamine, the more benzene rings you're adding to the nitrogen, but more you are decreasing. If you increase the benzene rings, then you are decreasing the basicity, because you are forming more chances of resonance, and you are involving the lone pair of electrons into more resonance with the rings. So these are the least basic, followed by the diphenyl, and finally the aniline is much more basic than the di and the triphenyl amines. Okay, so this is the basicity. And from the basicity, we move to the first reaction, which is the formation of the salts. If you have an amine and you add an acid to it, you end up with the salt of the amine. And this is a very, very important reaction. Okay, let's look first at the basicity, the slides of the basicity, and then we will deal with the first reaction, which is formation of salts. So, as we've mentioned, the tertiary amines are more basic than secondary, than primary, than ammonia, and the aromatic amines have the lone pair of electrons in a parallel plane to the ring, so they are involved in the resonance of the ring, and they are not localized on the nitrogen. Accordingly, aromatic amines are much less basic than aliphatic amines. This is the resonance, and this is what we have mentioned. The more you add of the benzene rings, the less is the basicity of these compounds, and if you add an electron donating group to the benzene, you are improving the basicity, while if you add electron withdrawing groups, you are actually reducing the basicity of these compounds. Let's now discuss the salt formation. As I've mentioned, if you have an amine, whether primary or secondary, whether aliphatic or aromatic, and you add an acid to this amine, you will actually end up with a protonation of the nitrogen of the amine, giving a salt. Why is this reaction important, and why did we stop this reaction? Because this reaction forms a way of purifying your products. When you're performing an organic chemistry reaction, you do not care about the reaction as much as you care about a pure product. If you perform a reaction that gives a mixture of compounds that cannot be purified, then this is a useless reaction in case of drug synthesis. You actually study organic chemistry in School of Pharmacy to learn how to synthesize drugs. So if you cannot actually separate a product, if you cannot end up with a pure product, then this reaction is useless to us. It has no meaning to us. So methods of purification and the products of the reaction, if they are easily purified, then this is a successful reaction. If the product of the reaction is not easily purified, then this is not a successful reaction for us. And the salt formation is one of the very important techniques of purification of acids and bases in organic chemistry. If you form a salt, you can actually purify these compounds. How? It's a well-known fact that most salts are water soluble, while free bases or free acids are less water soluble, and they are most probably organic solvent soluble. They dissolve in organic solvents rather than aqueous medium. So if we use this to purify the compound, what we do is that once you end up with the product, you place your product in a separating funnel. What is a separating funnel? It's a regular flask, but it has a tap, it has a tube at the end of the flask, at the bottom of the flask, and it has a tap that we can use to close this tube, or we can open it so that the liquid or the solvent or the whatever is placed in the separating funnel can be obtained or can be released from the bottom of the separating funnel. And it has a stopper at the top that we can open or close. Now we have the separating funnel. We place our reaction in this separating funnel. So you add your reaction. It has the amine in it. And you have organic solvent. The amine is soluble in this organic solvent. If you add to this reaction mixture some hydrochloric acid. In this case, you have just formed a salt of the amine. You had your amine, you added HCl to it, you formed the salt. So now the salt will move from the organic solvent. You have two layers. One is the organic solvent and one is the water, the aqueous layer, the layer that has the water in it. Your salt now moves from the organic layer to the aqueous layer because salts prefer to dissolve as they are soluble in water rather than organic solvents. So now you have your amine in the aqueous layer in the form of a salt. You can open the tap of the separating funnel now and you can take your salt from the water, leaving the organic solvent layer having all the impurities in it, or most of the impurities in it. Now you have the aqueous layer containing your salts. All what you have to do is just to add a base to liberate the free amine. So you add something like sodium hydroxide or potassium hydroxide to liberate the free amine and produce sodium chloride. This is how we can use salts to purify amines from the reaction mixture to a certain extent. This way you can actually perform one or two crystallizations to purify the amines from any other impurities. However, if you use the amine coming directly from the reaction mixture, you would have to use several times of crystallization and purification in order to purify your amine. The same applies to acids. This same technique applies to acids. However, you will reverse the order of addition. Again, you will have your reaction mixture and it's present in an organic solvent. It has the acid, the carboxylic acid in it. Now you need to form a salt from the acid. So you're not going to add another inorganic acid. You cannot form a salt from carboxylic acid by adding hydrochloric acid. What you actually need now is the sodium hydroxide. You add the base to produce the salt. So what you add is sodium hydroxide. You will have two layers. One is the organic layer and one is the aqueous layer, now having the salt of the carboxylic acid. Separated in a flask, you have an aqueous solvent containing your salt of the carboxylic acid. Add some hydrochloric acid to it to liberate the free acid. So you can use this technique to purify amines or any basic compound that we have in organic chemistry, and you can use it to purify any acidic compound. It depends on what you will add at the beginning. If your compound is acidic, then you add a base to first separate it in the aqueous layer to form the salt and separate your compound in the aqueous layer, and then you add an acid to liberate the free compound. If you're starting with a base, you add an acid to first form the base, to first form the salt, and then you add a base to liberate your free compound. This is the first type of reaction, which is the salt formation. The second reaction that can be performed by amines is the alkylation of amines. You can actually react amines with alkyl halides to alkylate them, giving the secondary and the tertiary amines. And we have a reaction that is very much related, which is the acylation. So we have the alkylation and we have the acylation of these compounds, where instead of using an alkyl halide, you use an acid halide. This, when reacted with amines, will produce the amides. So you can produce an amide through regular acylation of amines. A very much related reaction is the sulfonation. So the acylation is a type, and the second type is the sulfonation of these reactions, where you actually react your amine with the sulfonic acid. say we use sulfonyl chloride, benzene sulfonyl chloride. What happens is the same. You will have an attack of the amine on the sulfur, releasing the halogen, giving the sulfonamide. This is the structure of the sulfonamide. And if you remember, this is very much closer to imides. You have a hydrogen attached to a nitrogen, and the nitrogen is attached to two double bonds. We have an atom and two double bonds. It's exactly the same as in case of phthalimide. As we mentioned, you can remove the hydrogen, placing a negative charge, which is stabilized by resonance to both carbonyls. In case of sulfonamides, you will have the two double bond oxygens on the same atom. You do not have two carbonyls, you have a sulfonamide group, a sulfonic group. So now if you remove this hydrogen, placing a negative charge on the nitrogen, again you will have two resonating structures with each one of the oxygens. So this hydrogen is acidic and you can remove it using any base. N carrying a negative charge and the R of the amine. How do we use this reaction? This is a very famous reaction. It was invented by a scientist whose name is Hinsberg. Hinsberg reaction. Hinsberg, as a scientist, he actually used the sulfonamides to differentiate and to separate primary from secondary from tertiary amines. How do we do that? Let's look at each one of them. If you react the sulfonic acid or the sulfonyl chloride with the primary amine, you will have exactly the same reaction as we have mentioned. You will have the amine substituting the halogen in the sulfonyl chloride, giving a product which will precipitate. If you add some sodium hydroxide to this product, as we have mentioned, you have an alpha acidic hydrogen here, you have an acidic hydrogen on the nitrogen here. So adding a base will remove this hydrogen, giving the salt, which will be soluble. So you will perform the reaction by adding the amine to the sulfonyl chloride. You will have precipitated. If you add some sodium hydroxide to this precipitated, it will dissolve. However, if you are using a secondary amine, you will get the precipitated exactly the same as the primary amine. However, the nitrogen here is carrying no hydrogens, so we do not have an acidic hydrogen to replace. So you will see the precipitated. However, if you add sodium hydroxide, it will not dissolve. It will stay insoluble because you cannot form a salt. Finally, if you react the sulfonyl chloride with the tertiary amine, the nitrogen here has no hydrogens, so it will not perform this reaction. It cannot react with the sulfonyl chloride because it has no hydrogen to lose, like in these two cases. So you will not even get a precipitate. So if you have three bottles, one contains a primary amine, one contains a secondary amine, and one contains a tertiary amine, and you cannot actually know them from each other, you cannot specify which is the primary and which is the secondary and which is the tertiary, what you do to separate them or to recognize them or to identify them is that you add a drop of sulfonyl chloride. You take 1 ml from each of these bottles and you add a drop of sulfonyl chloride, benzene sulfonyl chloride to them. If you see a precipitate, then this is either a primary or a secondary amine. If you do not see a precipitate, then this is a negative reaction and this is the tertiary amine. Now, if you see the precipitated, we still don't know whether it's a primary or a secondary. It can be a primary or a secondary amine. What you do is that you add a drop of sodium hydroxide to this, or 1 milliliter of sodium hydroxide to this precipitated. If it dissolves, it's a primary amine. If it does not dissolve, then it's a secondary amine. This is how you can actually differentiate these compounds using the Hinsberg technique. How can we separate them? It's exactly the same. You will add the benzene sulfonide chloride to the whole bottle. If they are mixed together, if you have primary, secondary, and tertiary amines mixed together, add benzene sulfonide chloride to them. And then you will obtain a precipitated. You will have a flask that has the primary, secondary, and tertiary amine present together. Just add the benzene sulfonide chloride to this reaction. You will end up with a precipitated plus a supernatant, a solution, a precipitated and a liquid. If you filter this precipitated on the filter paper, the precipitated is the primary and the secondary amine in the form of the sulfonamide, while the supernatant that will be obtained after the filtration contains the tertiary amine. So now you have separated the tertiary amine. Just hydrolyze the sulfonamide and you this way have obtained the tertiary amine in a pure form. Now we have the primary and the secondary together. All what you need to do is to add some sodium hydroxide to them. And again, filter. Now the precipitated is the secondary amine because it will not dissolve when you add the base. And the supernatant is the primary amine because it will dissolve once you add a base to it. This is how you can use Hinsberg to separate or differentiate primary, secondary, and tertiary amines from each other. The fourth reaction is the reaction with nitrous acid. What is this reaction? It's the formation of the diazonium salt. We will deal with it in full details in case of diazonium salts. However, we have to mention it here, how this reaction proceeds. When you have a primary and aromatic amine, it has to be a primary and it has to be aromatic. Primary and aromatic amine. And you add nitrous acid to them. You will end up with the diazonium salts. First of all, we need to mention something here. First of all, there's nothing called nitrous acid. There's no reagent present in laboratories which is called nitrous acid because it gets quickly oxidized into the nitric acid, so we do not keep nitrous acid in laboratories. How do we get nitrous acid? We prepare it in situ through reaction of sodium nitrite with hydrochloric acid. The product is the sodium takes the chloro, giving the sodium chloride, and the hydrogen attaches itself to the nitro group, giving the nitrous acid. It is prepared in situ, within the reaction. Inside your test tube, you prepare the nitrous acid within the reaction, and it immediately reacts with your amine, because if it stays unreacted, it will get oxidized to nitric acid. So this is the first precaution. You cannot use nitrous acid. We do not have nitrous acid. We actually use sodium nitrite in presence of any acid. The simplest is hydrochloric acid. Secondly, you have to perform the reaction at 0 to 5 degrees centigrade. You cannot raise the temperature than 5 degrees, and you cannot allow the temperature to decrease than the 0 degrees centigrade. It's preferred, or it's obligatory for this reaction to be performed at 0 to 5 degrees centigrade, otherwise you get different products. Finally, you cannot use the aliphatic amines for this type of reaction. Why is that? When you add the sodium nitrite, HCl, to this reaction, even if you're performing the reaction at 0 to 5, you will get, it's true, you will get the diazonium salt. However, it's very unstable, and it loses a nitrogen molecule, giving the alkyl group as a positively charged moiety, which reacts with the hydroxyl group of the water, giving the alcohol. So if you actually try to prepare diazonium salts from aliphatic amines, you will end up with the alcohol and not with the diazonium, without any interruption from your side, without any, you don't have to do anything, it will end up with the alcohol. It will remove the nitrogen and put an alcoholic group in its place. So this is the fourth reaction, which is the reaction with the nitrous acid to give the diazonium salt. As I have mentioned, it has to be a primary and aromatic. The secondary gives a totally different product, and the tertiary gives a totally different product. If you allow the temperature to decrease than 0 degrees or increase than 5 degrees, this will produce a totally different reaction or a totally different product. And if you use an aliphatic amine, you will end up with the alcohol. The fifth reaction is the reaction with the isocyanates and the isothiocyanates. What are these? Let's first see where the name is coming from. This is a cyano group, so we say that this is cyanide. In case of the cyano group, the carbon is what is attached to the alkyl chain. In case of isocyanates, the nitrogen will be attached to the R. So what you're doing actually here is a positional isomer. You're actually putting the nitrogen in the place of the carbon and putting the carbon in the place of the nitrogen. So it's an isomer, so we say that this is an isocyanide. If you add an oxygen to the carbon, it becomes an isocyanate. Whenever you have an oxygen, you add the word ate at the end. So this is the isocyanate, and you just put a double bond between the carbon and the nitrogen to fulfill the valency of the nitrogen to be trivalent. So these are the isocyanates. When you react them with primary amines, remember that you have a carbon that is doubly bonded to an oxygen and doubly bonded to whatever on the other side, to another electron withdrawing or electronegative group on the other side. So this carbon is carrying a highly partial positive charge. The lone pair of electrons of the nitrogen of the amine will attack it, breaking the bond between the carbon and the oxygen and attaching the amine to the carbon. This bond reforms, breaking the bond between the carbon and the nitrogen, giving the substituted urea compounds. These are the product of the reaction with of the primary amines with the isocyanates. What are isothiocyanates? If we isothiocyanates, what we have added here is just the thio part. The thio part means that instead of having a double bond O, you're having a double bond S. So these compounds are exactly the same, but instead of C double bond O, it's a C double bond S. And your end product will be, instead of a double bond O here, it will be a double bond S. So it's a thiourea rather than a urea. So these reactions give substituted ureas and substituted thioureas. The sixth reaction of amines is reactions with aldehydes and ketones. This reaction, you can refer to the videos of the aldehydes and ketones for its details. However, we're just going to go through it quickly. What you have is, if you have a primary amine and you reacted with a carbonyl compound, you will end up with, first of all, attack, breaking the double bond here, and then you will have a full condensation, giving the imine, where you have a double bond between the nitrogen of the amine and the carbonyl of the aldehyde or ketone. Whatever is attached here, it's not our problem. You can just re-add it as such. So this is how the reaction proceeds in case of primary amines. However, if we use a secondary amine, the first step will be exactly the same. and you will have the amine attached to the hydroxy form of the carbonyl compound. Now your nitrogen has no proton, has no hydrogen, as in case of the primary, because it's carrying now two R's. It's a secondary amine, so it will have no hydrogen to condense with the hydroxy group on the carbon of the carbonyl. So it's either you stop at this stage, or if the side chain of the aldehyde or ketone has an acidic hydrogen, it will condense with the hydroxy group, giving what we call ene amine. This is an ene and this is an amine. So these are the ene amines, where we have a double bond alpha to a secondary amino group. They are formed when you react a carbonyl compound having an alpha acidic hydrogen with a secondary amine. If you reacted with a primary amine, you will not get the enamine, you will get the imine. You will have the double bond between the nitrogen and the carbonyl. However, if the nitrogen is carrying no more hydrogens, as in case of secondary amines, you will have the condensation on the other side of the carbonyl with the alpha acidic hydrogen. If the side chain doesn't have an alpha acidic hydrogen, the reaction will stop at the hydroxy compound. Finally, if you react these compounds with tertiary amines, you will get no reaction. This reaction cannot be performed on tertiary amines. The last reaction of the amino group is the mannich. If you remember, in part 1 of amines of nitrogenous compounds, the video part 1 of nitrogenous compounds, we said that if you use a secondary amine with formaldehyde with a compound that has an alpha acidic hydrogen in presence of inorganic acids, you will remove this alpha acidic hydrogen and you will add the CH2 of the formaldehyde and the nitrogen of the amine. For the exact detailed mechanism, you can refer to aldehydes and ketones, and you can refer to the part 1 of nitrogenous compounds, the video named part 1 of nitrogenous compounds. Let's now look at these reactions on the organized slides. As we mentioned, the first reaction of the functional group, which is the amino group, is the salt formation, and it depends on the presence of the lone pair of electrons on the nitrogen, resulting in basicity of these compounds, and they can be used to separate amines and purify amines from other compounds. It is formed through adding an inorganic acid to amines, resulting into the salts of the amine. As we said, the salt of the amine is usually water soluble. We can react amines with alkyl halides, resulting into alkylated amines, secondary or tertiary, and we can react them with acyl groups like acid halides or anhydrides, resulting into the acid amides. And finally, we can react them with the sulfonyl chlorides, which is again some sort of an acid. It's an acid compound or an acid derivative. It's regarded as an acid derivative of the sulfonic acid, and you will end up with the sulfonamide. As we said, in case of primary amines, you will have a hydrogen attached to the nitrogen after the formation of the sulfonamide, which can be removed by a base producing the salt, which is water soluble. In case of secondary amines, you will end up with the sulfonamide having no hydrogen, so if you add a base, it will not dissolve. The precipitate that was formed, which is the sulfonamide, will not dissolve. And finally, in case of the tertiary amines, the reaction will not proceed whatsoever. Afterwards, we dealt with the reaction of primary aromatic amines. As I've mentioned, it has to be primary and it has to be aromatic amines with nitrous acid, which is produced in situ through reaction of sodium nitrite with hydrochloric acid at 0 to 5 degrees, giving the diazonium salts. And as we've mentioned, aliphatic diazonium salts are unstable, giving the alcohol. Reaction with isocyanates and isothiocyanates. end up giving the substituted ureas and the thioureas. Reactions with aldehydes or ketones, as we have mentioned, if you're using a primary amine, you will end up with the imine. However, if you are using a secondary amine, you will end up with the enamine, and this is the mechanism of the reaction. Mannich reaction, this is the mechanism. You can refer to its explanation and details in aldehydes and ketones videos and in the part 1 of nitrogenous compounds videos. As we've mentioned, you will use formaldehyde, secondary amine, and a compound that has an alpha acidic hydrogen, and you will end up adding a CH2 amine in presence of the alpha acidic hydrogen. Now we move to the reactions of the side chain, which are the reactions of the benzene ring. Our side chain now is the benzene ring. What are the reactions of the benzene ring? As we all know, benzene ring can perform electrophilic substitution reactions and nucleophilic substitution reactions. For the nucleophilic substitution reactions to proceed, you have to have an electron withdrawing group on the ring, placing a positive charge in the ring. Since we are now dealing with amines, which are electron donating groups rather than withdrawing, so you cannot perform the nucleophilic substitution reactions. You will only deal with the electrophilic substitution reactions. What are the electrophilic substitution reactions that you know? These are the nitration, sulfonation, halogenation, and Friedel-Crafts reactions, whether alkylation or acylation. If you refer to the videos of the aromaticity, you will find that one of the limitations of Friedel-Crafts reactions are the amino group on the benzene ring, where the nitrogen has a lone pair of electrons and you're actually using a Lewis acid like aluminium chloride or ferric chloride. So the nitrogen donates its lone pair of electrons in the vacant orbital of the Lewis acid, damaging the catalyst that you are using, and accordingly this reaction cannot be performed. So Friedel-Crafts are not applicable to anilines or to aminobenzenes. So we only have the 3 other types of reactions, which are the sulfonation, nitration, and halogenation. Let's first deal with the easy ones. In case of nitration, if you remember in part 1 of nitrogenous compounds, we said that if you have an amino group, the ring is highly activated and you will end up with the mono, di, and tri-substituted benzene in addition to an oxidation product. So how did we solve this problem? We solved it by acylation. We performed first acylation of the amino group to distract the lone pair of electrons between the ring and the carbonyl, and then we perform the nitration, and then we hydrolyze the acyl group. And as we said, you end up with a para product as a major product. Then you hydrolyze to end up with the nitroaniline. Para product is a major product. The same applies to the halogenation. When you perform halogenation of the aniline, you will end up with a multiple substituted compound due to the high activation of the ring rather than a mono substituted compound. So to solve this problem, again you use the acylation of the amino group, and then you perform the halogenation, giving the para product as a major product, and then you hydrolyze the acyl group, giving your final product. Just one nota bene here, you cannot use, when halogenating Lewis acid, you cannot use aluminium bromide. It will be destroyed by the lone pair of electrons of the amino group. So what do we use? We use water, just bromine water, bromine in water, and you will end up with your product. Now we have the final electrophilic substitution reaction of the ring, which is the sulfonation. We have already discussed the nitration and the bromination or the halogenation, and we said that all what you need to do is just acylate the amino group to reduce the donation power of the amino group. and end up with your required product. Finally, in case of sulfonation, we have the same problem, which is that the ring is highly activated. And we have an additional problem, which is you are going to be adding an acid. This problem applies in case of sulfonation and nitration. You have a problem, which is you're adding an acid. So once you add an inorganic acid to amino compounds, you will actually end up with the salt. You will not have the free amine. You will end up with the salt. Once you obtained the salt, now the nitrogen is not carrying a lone pair of electrons. On the other hand, actually it's carrying a positive charge. It's not carrying a lone pair of electrons. It's actually carrying a positive charge. So it's no longer an electron. Here, the nitrogen is an electron donating group. However, when it carries a positive charge, it's an electron withdrawing group. So the reaction, if you allow the reaction to proceed, you will your end up product will be the metasulfonic acid, of the amine. So this is not what you actually need. What you need is the ortho or the para. If you actually need the meta, then this is a perfect reaction. Just use fuming sulfuric acid and stay at room temperature. If you do that, you will end up with the meta-substituted amino compound. However, if your target compound is the ortho or the para, like we are usually used to do, if we need an ortho or a para substituent, we use an electron donating group. So if we're actually starting with an amino group, then we were targeting the ortho or the para. You have one of two solutions. It's either you acylate, like you did in case of nitration and halogenation, you acylate your compound, and then you sulfonate your compound, and then perform a hydrolysis step, which are too many steps. If you look at this type of solution, you actually performed an acylation, this is a one step, then a sulfonation, which is a second step, then a hydrolysis, which is a third step. Each step will need purification, and each step will reduce the yield of the final product. However, in case of sulfonation, we can actually solve this problem without going through all this technique. How do we do that? You can actually take the aniline and you can react it with the sulfuric acid. However, you will heat at 160 to 180 degrees centigrade. The first step, as we have mentioned before heating, first of all, the aniline will react with the sulfuric acid, giving the salt, which we actually expected. However, we are actually heating at 160 to 180 degrees centigrade, so we lose a molecule of water, giving the sulfonamide. You have now the NH, and then attached to the sulfonamide group. This way, you have the lone pair of electrons on the nitrogen. They are donated to the sulfonamide in a resonance, in two types of resonance, and they are donated to the ring. So this is something very much close to acylation. In acylation, you distracted the lone pair of electrons here between a carbonyl and the ring, and now the nitrogen is not basic enough to be protonated and to form the salt. The same applies to the sulfonamides, but to a much better extent, because the sulfonamide is not one carbonyl, it's regarded as if it's two carbonyls, where the sulfur is doubly bonded twice to two oxygens. So now the lone pair of electrons on the nitrogen is a third of the time given to the benzene, and third of the time in a resonance with this oxygen, and third of the time is in resonance with the other oxygen. Now the sulfuric acid will sulfonate this compound at the para position, and then you can hydrolyze this compound. If you look at this reaction, you have actually done two reactions rather than three. In case of acylation, you have performed acylation, sulfonation followed by hydrolysis. In case of using the consulfuric acid and heating at 160 to 180, you have actually performed just the sulfonation followed by the hydrolysis. So you have lost one step where you actually formed the sulfonamide rather than the acid amide. To do this, you use regularly the sulfuric acid as you are commonly used to do in case of sulfonation, but raise the temperature to 160 to 180 to lose the molecule of water and end up converting the salt into the sulfonamide. Let's look at these slides. As we have mentioned, in case of sulfonation, we use sulfuric acid, whether conc or fuming. Fuming is a more vigorous sulfuric acid because it has sulfur trioxide gas bubbled in it, but make sure you use it at room temperature. This way you end up with the salt, which has a nitrogen carrying a positive charge on it. Accordingly, it's an electron withdrawing group rather than an electron donating group, and thus it directs the sulfonic group to the meta position. However, if you use the sulfuric acid at 160 to 180, and in this case it's useless to use fuming sulfuric acid, because once you heat you will lose the sulfur trioxide gas. So no way to waste your money and use fuming sulfuric acid. Just use conc sulfuric acid. First step will be the salt formation, but once the heating starts, the salt will change into the sulfonamide, which will sulfonate the benzene at the para position, and then we hydrolyze to get the free amine. As we mentioned, in case of nitration, you need to acylate first to prevent the salt formation here and to prevent the high activation of the ring. Once you've formed the acid amide, you perform your nitration and then you hydrolyze your product. And in case of halogenation, as we have mentioned, again, if you perform direct halogenation, you will end up with the tri-substituted product. So you have to acylate first, forming the acid amide derivative, and then you halogenate to get the para-bromo product, and then you hydrolyze your compound to get the free amine once more. But remember not to add the Lewis acid, because if you added Lewis acid to this reaction, then you do not understand anything from what we have said. You use bromine water and no Lewis acid, so that the lone pair of electrons of the nitrogen are not donated into the vacant orbital of the Lewis acid. This way we have finished the amines as part 2 of the nitrogenous compounds, and next video will deal with the diazonium salt as the last group of nitrogenous compounds.